Welcome back. Today's topic is logarithms. If you don't have any experience with these yet, they can be a little bit weird and a little bit tricky. So hang in there and you can do this. But it might require a little bit of work and some definite headache trying to get your mind to wrap around some of it because it can be a little bit weird. So hang in there and we'll get there. If you have seen these before, then you kind of know what I'm talking about. But here we go. What is a logarithm? Well, here we go. A logarithm, let's say we have y is equal to the log base b of x. This is equivalent to saying that b to the y is equal to x. Basically what we have is that y is the exponent that would need to go on b to give us x. So what a logarithm does is it spits back out an exponent. Okay, and that's really going to be one of the best ways we can think of these. So I have over here an example, and you'll see it's kind of a circular example, and we'll see why here in just a second. So I have the log base 3 of 81 is equal to 4. This is true because, or since, 3 to the, there's my exponent, 3 to that 4th power is equal to 81. So what we have here this is what we call logarithmic form. And so we could take something that's an exponential form and change it to logarithmic form. Or we can take a logarithm and we can change it into what's called exponential form. And so you want to get really good at rearranging these pieces to go back and forth between logarithmic and exponential forms. Notice the base is the same for both. Okay, this number down here on the log is still called the base. But now the exponent's on the other side of the equal sign, and down here it's actually an exponent. And here the 81 is inside of the logarithm, and down there in exponential form, 81 is the answer to the exponential. So you're going to want to really try and work on going back and forth between those. It's going to come in really handy in a couple of sections when we start solving equations. But let's see what else we can do with logarithms for now. All right, so next up, exponential and logarithmic functions that have the same base are inverses of each other. That's super important, super useful. And basically it's because of how they're defined, but here's what happens. Let's say we have f of x is log base b of x, and g of x is b to the x power. So I have a logarithmic function and an exponential function, both with a base of b. Now, if I do the composition of functions, because these are inverses, so you can see what happens. Oops, I forgot a bracket. There we go. I put g inside of f. G of x is b to the x, so I replace it with its rule. So we have f of b to the x. And then that says, hey, take whatever is inside and replace x with it. So we get log base b of b to the x is equal to x. It makes sense, but it also works because they are inverses. Okay? Because they are inverses, remember, if you do a composition of inverses, you have to get x out. And it works the other way. Now if I put f inside of g, I replace it with its rule, log base b of x. And when I plug that into g, I get b raised to the log base b of x power. That looks weird, but again, because they are inverses, it has to be equal to x. All right, so we're going to put this to use now. We're going to move on and we're going to make some graphs with logarithms. Again, just like with exponential functions in the last section, I'll do a really nice, simple example, well, relatively simple example, and then I'll make it a lot more complicated. And we'll see what we have. So let's go. All right, so here I'm going to make what is a relatively simple logarithmic graph. So I want to graph y is equal to log base 3 of x. Okay, nothing there to mess it up or make it harder, just a nice straightforward logarithm. But here's the key to these. Nobody likes logarithms. So we're going to try very hard not to actually have to work with a logarithm. It's so much easier to think in terms of exponential functions. So here's how we can make that work. Because they are inverses, remember with inverses, all that happens is that your ordered pairs are switched. So if I plug in numbers for y, which maybe you can read that, that's kind of some chicken scratching down there. But if we plug in numbers for y, we can do an exponential function going backwards to x. And that works again because these are inverses, so their ordered pairs are just backwards from each other. So with exponential functions in section 4.2 that we looked at, hopefully recently, we noticed that, or I said I wanted you to see you plug in 0, 1, and -1. I still want you to do that here for logarithms, but it works so much better if you plug them in for y, because now we can do an exponential function. In fact, you can't do them for x here. That would blow it all up. We'll see why in just a second. So going backwards, 3 to the 0 power is 1, 3 to the first power is 3, and 3 to the negative first is a third. And this is a much easier way to come up with some really nice points. A lot of times people just start throwing x values at this, and I get some really hideous numbers, and those are hard to graph, they're kind of a pain. So much nicer if you do it this way. So let's see what it looks like. First of all, we have a vertical asymptote. That is because these are inverses. So with an exponential function, you could not get any y values out that were 0 or negative. That means if we switch the ordered pairs, you can't plug in any x values that are 0 or negative. Okay, in fact, we're going to go one step further and say that our domain for a logarithm is that x has to be strictly greater than 0. You cannot plug anything negative into a logarithm. So then I took my points, 1, 0, 3, 1, and 1/3, -1. I plotted them. And then the shape of a logarithm is that it's going to come up, well, either up or it could come down, depending on your base. It's going to come up here along my vertical asymptote. It's going to hit those 3 points, and it's really, really going to level off. If you think about it, we're asking 3 to what power gives us something. So in order to get 2 out, which would be the exponent, 3 squared, right? Remember that the answer to a logarithm, the y value here is the exponent. 3 squared is 9. So to get up to 2, you'd have to go all the way out to 9. All right, so we're going to do a harder one next. Here we go. All right, so here is our more complicated example. I want to graph y equal to -2 log base a half of x minus 1 plus 3. That is a big mess. So again, like I did with the exponential functions in section 4.2, I'm going to break it down into smaller bits. So the first thing I want to pay attention to is that this 3 at the end is going to move the whole graph up 3, and the -1 on the inside will move the whole graph to the right 1 unit. And so you can see what I have here. You can see the whole graph, but the really important bit right now are those dotted lines. Okay, again, if we make those shifts first, so up 3 and right 1, if I make my graph in relation to these dotted lines as my fake axes, I don't have to worry about those numbers anymore. I just plot all my ordered pairs in relation to those, and I will have the correct graph. All right, so now let's go find those ordered pairs. So we have here x, and I want to start with a simpler y. I want to start with just log 1/2 x. Okay, so I want to ignore that -2 for just a second. You'll notice I have x, I have that log 1/2 x, and then over here I do have the -2 times that. So again, I'm going to do something similar to what I did with the exponential functions. I'm going to plug in 0, 1, and -1, but again, because this is a logarithm, I'm going to plug them in for my initial y values here. Okay, I plug them in for that log 1/2 x, just a plain normal y. So going backwards using an exponential, 1/2 raised to the 0 power is 1, 1/2 to the first is 1/2, and 1/2 to the negative first is 2, the reciprocal of 1/2. So then we can deal with that -2 by just remembering, okay, that's going to multiply all my y values. 0 times -2 is 0. 1 times -2 is -2. -1 times -2 is +2. And again, these will be my ordered pairs. I don't need that middle column anymore. So I know that we want 0, 1, and -1, but here they're just a stepping stone to help us to our to the ordered pairs that we want. So again, I plugged them in for y. I used the exponential function to go backwards. And then I multiplied all those by -2 to get the graph that we really need because of that -2. All right, so then I plot them. There's 1, 0. Again, it's in relation to my dotted axes. So I have these dotted lines. There's my 0, 0. So there's 1, 0. I have a half, -2, and I have +2, +2. There's my 3 points. Again, it's going to come along the vertical asymptote, hit the 3 points, and it's going to really level out a lot, but it will grow forever. It just gets really, really flat along the way. And there we go. That's a logarithmic graph. So go back and watch this video again. Pause it if you need to. Figure out what the heck is going on, because they can be a little bit weird. All right, we have a little bit more to look at here before we call it a day. All right, a few more things with logs. First, the domain. The inside of the logarithm has to be bigger than 0. So for example, f of x is equal to log base 4 of x minus 5 plus 1. The inside, the x minus 5, for the domain, x minus 5 has to be bigger than 0. Or in other words, x has to be any value bigger than 5. You can never plug a negative number or 0 into a logarithm. It doesn't work. All right, a couple other things that are really fun. Common log and natural log. Common log is base 10. And it's so common, bad joke, so common that we don't even write the base. This is a button on your calculator. So if you're looking at your calculator and you see this button that says log, it has to be base 10. If you try to use that for any other base, it will never work. But it does work for base 10. So the common log of 520, if you type it into your calculator, is about 2.7. There are a lot more decimal places. The other really important log is what's called the natural log, and the natural log is base e. We write that as just ln x. And again, that's a button on your calculator. So if you need to find the natural log of something, you can use that button. But what about other bases? What if you had base 13 or something like that? Let's take a look. All right, so next up, what if we want to find something like the log base 13 of 5,920? So you can see my math here. I already did the problem, but let's see where this comes from. It comes out of something called the change of base formula. This is for when you have a base that you can't evaluate. So what it does is says log base a of x. If you want to change from a base of a to a base of b, you do log base b of x, and then you divide by log base b of the original base a. Now, some of you have on your calculators the ability to do any base you want. So if you have a newer calculator, go look under the math button. It should be there. My calculator doesn't have it. I have to do the change of base formula to find these. If you can find that, go ahead and use it. It's definitely nicer and easier. If you can't, you're going to have to use change of base formula. All right, log base 13 of 5,920. So I chose to use the common log, base 10, right? So there's no base written. That means it's base 10. So I typed in log of 5,920 divided by log of 13. It gave me 3.4. Now you have to be really, really careful. When you type it into your calculator, it will give you a parenthesis for that 5,920. You have to close it. Otherwise, your calculator will do the order of operations perfectly, but in this case, incorrectly. So it'll do the 5,920 divided by this, and then it would take the log. That's not how we want it. So you really have to make sure to be careful and close that parenthesis around there. And if you do that, you'll be all set using your calculator. So good luck with logarithms. Don't worry, we're not done with them yet. We have more to do. I can tell you're excited. I am. So anyway, good luck and have a great day.